For the past decade, agricultural technology has been trapped in a honeymoon phase. We saw a flood of venture-backed prototypes and fully autonomous concepts that looked perfect in digital pitch decks. But that laboratory perfection falls apart the moment it hits the dirt. The physical reality of farming is defined by choking dust, unpredictable biological chaos, and extreme weather that ruins delicate hardware. Operators are also dealing with tightening margins. They face severe, compounding labor shortages, alongside rising costs for fertilizer, seed, and chemical inputs. Out in those fields, connectivity is rarely reliable. Cloud-dependent AI models that worked beautifully in an office fail completely when a tractor hits a Wi-Fi dead zone during a tight, unyielding harvest window. The agricultural environment acts as a brutal filter for technology. If a system only functions in a controlled setting, it becomes effectively useless to a grower. Farmers and agribusinesses have moved past the era of experimentation. The conversation today is about strict economic accountability. This chart shows the sharp decline in general AgTech venture funding against the steady upward trajectory of practical AI tools. Operators now require explicit proof that a tool reliably offsets a cost or protects yield over an entire season. Modern buyers prioritize measurable economic defense over the excitement of a new gadget. To survive poor rural connectivity, the industry has turned to edge AI, computing that happens locally, right at the source of the data. This diagram illustrates how processing data directly on the tractor node works, explicitly severing the connection to a distant cloud server. This allows the machine to make zero-latency decisions in the field, even when cell service drops completely. Localized processing power supports predictive growth modeling. Instead of waiting for a threshold alarm to fire after a crop is already stressed, the system forecasts changes and prompts proactive adjustments to irrigation or canopy temperature. These models focus on resource efficiency rather than total human replacement. They detect pests early and pinpoint exact water and fertilizer needs, significantly reducing expensive chemical inputs. Invisible decision support integrated into the background provides far more utility than a high-profile robotic replacement. Delegating high-stakes crop decisions to an algorithm creates serious operational and ethical risks, especially when the AI operates as a black box that humans can't easily audit. When operators rely entirely on algorithmic recommendations, we see the degradation of generational instincts and localized knowledge. Simultaneously, large entities can bundle AI with patented seeds, forcing farmers into long-term dependency on closed ecosystems. Preventing this trap requires structural solutions. Systems need to be designed around human-AI collaboration and knowledge preservation programs, ensuring the technology assists the workforce rather than de-skilling it. Long-term technological value empowers the operator's autonomy. If it overrides their control and locks them into an inflexible ecosystem, it becomes a liability. Right now, the market consists of hundreds of independent startups offering isolated solutions, but that fragmented landscape is rapidly consolidating. Buyers are engaging in capability shopping. Major manufacturers are acquiring specific, proven AI tools to plug gaps in their own product stacks. For instance, equipment manufacturers are buying aerial scouting and computer vision companies. They integrate these analytics into existing hardware ecosystems, keeping farmers inside their workflow. For an independent AI tool to survive today, it must plug effortlessly into the farm management systems growers already use. Established distribution networks and workflow integration are now as critical to an AI product's survival as the underlying code. Agricultural AI has evolved. It began as a fragile laboratory experiment and has been forced into becoming a rugged utility. The ultimate stress test for these systems is multi-season retention. The technology has to survive a bad weather year, tightening budgets, and operator fatigue, and still convince the farm to renew their contract for the next cycle. In high-stakes, unpredictable environments, the novelty of a tool matters far less than its ability to reliably survive the season.